Each of these cars is controlled by an artificial intelligence in Trackmania, and this AI has only one goal: to drive as fast as possible while keeping its balance on a pipe. But as you'll see, driving on a pipe is not as easy as it looks in this racing game. In this video, I will show you how I built this AI using machine learning. I will first test it on a straight pipe, and then I'll try to increase the difficulty. And finally, I'll compare my AI with some top level players in order to see if it can keep up with their pace. I've been working on AI projects in Trackmania during the last few months, and so far I only trained AI to drive on basic roads, which seems more natural than having a car driving on a pipe. But Trackmania is not only about flat and monotonous roads. For years, players have been building a huge variety of maps using thousands of different building blocks, so it was time for my AI to explore the game physics a bit more. Unfortunately, it will be very complex for an AI to master all these different blocks and driving styles at the same time, so I had to make a choice. The pipe block was originally intended as a decorative element, but it has always been used by the Trackmania community as a road surface. And keeping the car balanced on this surface can be very complicated for beginners. On the other hand, an AI could have some advantages in this challenge. Driving on a pipe in Trackmania is a very specific task, and this is well suited to machine learning and AI, which often work well for very specific problems. To keep things simple, my first goal will be to create an AI that can cross this long straight pipe without falling in the water. When playing Trackmania, a normal player will generally use his eyes to identify different elements on the screen, where his car is, which paths to follow, or which obstacles to avoid, and he will make a decision based on what he sees. However, my AI has no eyes and it can only recognize numbers. A computer screen simply represents a set of pixels that can each be represented by numbers, so I could directly give the value of all these pixels to the AI. The problem is that even at low resolution, an image usually contains thousands of pixels. Here, you don't need that much data to describe how a car is positioned on a straight pipe. In fact, I'd like to describe as many elements of the game as possible using as few numbers as possible. This way, it will be way easier and faster for the AI to learn something. So the AI will only have access to 7 values, which I will call inputs. First, it gets 2 values that describe how the car is positioned on the pipe. AI also knows the car speed and the car acceleration. And the 3 last inputs describe the inclination of the car. AI can control the car direction by simulating a gamepad joystick, and it can also choose whether the car accelerates or not. These actions correspond to what the AI decides to do and are called outputs, and I'm not adding the brake for now because it's not very useful on a straight pipe. Now that I have defined inputs and outputs, here is a short explanation of how the AI will work in practice. I am running both Trackmania and a computer program I wrote at the same time. The game continuously sends information to the program using a software called OpenPlanet. OpenPlanet provides some access to the Trackmania API. This way, it is possible to get game data, and after that, these data are converted into valuable inputs. Once my program gets inputs, it tries to predict which game action is most appropriate using a model trained with machine learning. And finally, these outputs are directly sent to the game. Now, one key element still needs to be defined: how the AI actually learns to interpret inputs. For this, I have 2 possibilities. I could teach the AI to imitate the way I play using supervised learning, or I could let the AI learn everything by itself by trial and error. Here I prefer to try the second option. That way, it gives the AI more freedom to choose its own driving strategy. The AI is not limited by my own level of play, and in theory, it could even become better than me after enough training. So just like in my last videos, I will use a genetic algorithm. Basically, this algorithm works in the same way as natural selection. I first initialize the algorithm by creating 100 AIs. Each AI uses an artificial neural network to link its inputs and outputs, and each of these networks is randomly configured. As might be expected, most of these neural networks are completely worthless. But out of the large number of random AIs, a couple of them are able to keep their balance on the pipe for a few seconds. So I'll keep the best AIs and combine them with crossovers to form the next generation. To select the best AIs, I simply look at the distance they travel without falling up the pipe. I also add mutations in each generation. This means that I randomly modify the neural network of some AIs to maintain diversity. After only 8 generations, the AI manages to finish the map with a time of 20.57 seconds. It's quite slow compared to what humans could do, but AI is not going to stop there. From now on, if several AIs cross the finish line, they will also be ranked according to their time. This way, I want to force AI to take more risk in order to go faster. In generation 23, AI improves its best time by almost 3 seconds, finishing the map in 11.04 seconds. At this point, I was quite impressed with the AI's performance, but something even more interesting was going to happen a few generations later. So far, most AIs are using the same approach, the zigzag strategy, but in generation 25, one car is doing something different. In the first seconds, this AI does not move much and slides slowly towards the edge of the pipe. But at a specific moment, it starts to accelerate without turning. It turns out that the AI was waiting for its car to have the perfect angle so that it could drive straight without falling off. This is the all-in strategy. And with this new approach, the AI is able to catch up with its competitors and almost manages to finish in first place. As this different AI has performed rather well, it will have an impact on the development of the following generations. Now, a few AIs are experimenting with similar strategies and most fail quickly. But on generation 27, this new strategy is paying off again. 8.97. This time, AI is getting very close to my personal best time. The AI no longer loses time at the start and corrects its angle by turning slightly left at the start, which is the optimal strategy on this map. I let the algorithm run until generation 50 to see if the AI could do any better. Surprisingly, the all-in strategy disappeared as quickly as it arrived, and all the AIs are back to zigzagging. I think there are several reasons for this. The all-in strategy is much riskier and difficult to replicate, so it has difficulty spreading from generation to generation. I have also noticed that with this type of algorithm, it is quite rare for different strategies to coexist for long. And there is one last problem with what I did, which I didn't think of at first. In my approach, each neural network predicts the direction of the car as a number between 0 and 1. So to go straight, we need a value of 0.5. And the problem is that neural networks seems to have more difficulty in predicting intermediate values, and even a value relatively close to the center will result in a very slight turn, which can be disastrous when you want to keep a perfectly straight trajectory. So I decided to modify the AI slightly so that it can predict a third output, again between 0 and 1. If its value is less than 0.5, then the AI can turn, using the predicted direction, but otherwise the car goes straight. Adding this small modification, I had to retrain the AIs from scratch, but I quickly saw that this small change completely alters the evolutionary process. This time, all AIs are using the all-in strategy. After 4 generations, AI is already able to finish the map. In generation 14, it sets a new best time, and in generation 27, it even equals my personal best time, 8.74. Looking at all this, one might think that it's not so hard to go straight on a pipe, but that's already a good start. We just saw that AI can quickly learn different driving approaches by itself using a very limited set of inputs. And as long as it provides material for some nice video clips, I am still happy. At this point, I was happy with the AI's performance and rather confident that it will do just as well after adding a few turns to the pipe. But getting the AI to turn correctly was going to be a whole different story. Now, my goal is to train an AI that can complete this new map. The AI will have to pass a dozen corners without falling into the water. Driving on a pipe with curves is much harder, and finishing this kind of map can be quite challenging. With the inputs used before, the AI has no information about the pipe's path. So I need to add new inputs to allow the AI to locate itself in relation to the curves. So now, AI has access to the distance between the car and the next turn, and also the direction of its next turn. And from now on, AI can also use the brake. This time again, I wanted to see if the AI would succeed in this new challenge by learning everything by itself. So I'm once again using a genetic algorithm. After several dozen generations, AI has not learned much. It seems that there is too much for the AI to learn at once. So I chose to limit the speed of the car at first to make it easier, but it didn't work. Then I tried to change the reward system to add inputs, it still didn't work. So after trying all this, I decided to use a reinforcement learning algorithm called Deep Q Learning. It still didn't work. This is the part of the project where I spend the most time, but I won't bother you with all the details because it's a bit boring to watch cars fall into the water again and again. I think the main problem here is time. Training an AI to learn everything by itself usually requires a huge number of iterations. In Trackmania, I can only simulate the runs one by one at real speed. So whenever I want to test something new, I have to wait hours, even dozens of hours, before I can expect to get a result. At this point, I was also beginning to doubt my selection of inputs. Maybe the AI just doesn't have the right information to drive properly. To know for sure, it was time for me to give a little help to the AI and take it in the right direction. It was time to try another branch of machine learning that I mentioned earlier in the video and with which I'm a bit more familiar: supervised learning. This time, AI doesn't learn to drive on its own by trial and error. Instead, I will show the AI how I play and it will try to imitate me. This is how it works. First, I just drive on the map, trying to apply myself as much as I can. While driving, a program records the game inputs and the keyboard keys I press to drive. After driving for a few minutes, I already have 2000 pairs of input and output data. Then, I'm giving this data to the AI so that it can train its neural network. Basically, a neural network is composed of thousands of parameters. Each parameter can be tuned using some math to increase the prediction performance of the network. After a few minutes of training, AI seems to have learned the relation between my input and output data, and it's ready to drive for the very first time. That's it, the AI is finally able to turn. I find it pretty impressive, given that the AI has only seen a few minutes of human gameplay. However, the AI is not very stable yet, and it always ends up falling after a few turns. But in machine learning, it's generally accepted that the more data you have, the better the neural network you train will be. And 2000 pairs of data isn't that much. So, as it's very fast to collect data here, I want to see how the AI will perform after training on 100,000 data instances. After an hour of data recording and about 5 minutes of supervised learning, the final version of my AI is finally ready. Now it's time to see if the AI can finish this map. And also to have some fun, because as usual, the good thing about programming is that if you manage to automate something once, it's pretty easy to make it repeat 5,000 times. If I simulated so many runs, it was also to see how fast AI can go on this map. You may wonder why all these cars are taking different lines when they're controlled by the same AI. It's simply because all AIs don't receive the same inputs at the exact same time and with the same frequency. And then, a very small input difference at one moment can lead to a big difference a few seconds later. Also, I tested a dozen of different neural networks trained with slightly different parameters to fine-tune the AI. And after this last training step, here is the best time the AI has achieved. After seeing about 1 hour of my gameplay and using only 9 inputs, the AI can perfectly imitate the way I play, and it's even able to beat my personal best time. Well, if I had spent as much time playing this map as I did creating my AI, I could probably drive a bit faster. But instead, I asked a few players to send me their best run of this map to compare with my AI. This time, the level is a bit higher, but the AI does pretty well considering that most of these players have years of experience with the game. The map record is 38.67 seconds by Bluefeed, which is a very fast time. And it clearly shows the limits of supervised learning. My AI only learned to imitate me, and since my trajectories are not optimal compared to what Bluefeed does, AI has no way to drive faster than him. So the solution would be to make supervised learning from better runs or to return to other machine learning approaches such as genetic algorithms or reinforcement learning. It might even be possible to combine the two learning approaches. And of course, my AI only learned a small part of what driving is, and it cannot generalize its knowledge to other types of roads. But that was not my goal. Here, pipe driving is more like a toy example to demonstrate what artificial intelligence can do in a game like Trackmania. And it will be a long time before a computer program can completely match the skill and creativity of Trackmania players.